Pictured below is a position versus time graph for a moving object. I'm going to answer the questions below, and I'll see if I can sketch a rough graph of the velocity versus time and the acceleration versus time. So first of all, there are certain features that we look for in a curved motion graph to inform us about what is happening in the motion of the object. One of the things to look for is we want to look for critical points. These could be minimums or maximums, they're called. They're turnaround points for the graph. These will be places where the velocity of the object is 0. So let's take a look at our graph. Where do we have a minimum and where do we have a maximum? So right here at point B, this is what's called a local maximum. And when we have that, we found a place where the velocity of the object is 0. Now down here, we see point F is what is called a local min, or local minimum. And this is also a place where the velocity is going to be 0. So at what points is the object's velocity 0? At B and F, the turnaround points. It's where the object is changing its direction of motion. For example, on the way up, we were headed in the positive x direction. We stopped suddenly, and then when we return toward the negative direction, we've changed direction. And anytime you change direction, that means for an instant, your velocity has to be 0. Here we're headed in the negative x direction. We stop for an instant and then head back toward the positive x direction. So that is also going to be a point where the velocity is instantaneously 0. So now one of the things we may wish to do is try to sketch a velocity versus time graph. And this could be a tricky thing to do. But at least we can plot 2 points on here and just line them up and then make sure that your velocity value is 0 for this time. And then at this other time, we also want the velocity to be 0. Now we'll try to figure out what happens in between those points. At what points on the graph is the object moving slowly? So just as I had done before, we want to think about ourselves walking on the curve and see how steep it is, because the steepness of the curve tells us about the velocity. The more steep it is, the higher the speed. And the less steep it is, the slower the speed. So out of all the given points, A, B, C, D, E, F, and G, where does it look like we're on a hill which is not steep? We can't be at a valley or a peak, because then we wouldn't be moving at all. But we're looking for a place where the hill is very gradual. It's got a low, small slope. That would be places where we're moving slowly. E jumps out to me as a point where the speed would be slow. So I'll write that down. And let's see, anything else? Yes, perhaps point C. Point C looks like it has a fairly gradual slope. I'm going to put those two as my answers. Now, where do we think the object is moving fastest? Now we're looking for the steepest slope of all. I believe A is a good candidate. Maybe G, that's pretty steep, but I do believe A is steeper. So I'm going to put A as my answer to the fastest speed of all. Now we're asked, where is the object speeding up? We're looking for the slope to be getting steeper and steeper and steeper. Okay, so where are we speeding up? We already established that at B, the object's not moving, the velocity is 0. But at C, we said it was moving slowly. And I think at D, the slope is even steeper, which means it's moving pretty fast at D. So I would say on this whole interval here, this would be a place where we're speeding up. And there's one other place where we're speeding up. That would be from F to G. As you can see, if this were the profile of ground, it would be level there at the valley, but then it gets steeper and steeper, so it's actually speeding up here. But there's no exact point that I can put where it's speeding up on that interval, so I'll actually just answer with C, and that's my only answer for that. Now, where is the object slowing down? This would be a place where the slope is getting less steep. It starts off really steep, and then it gets more and more gradual as time goes on. Well, I think around here, here our slope is quite steep at A, and then it levels off. So we're slowing down here. Where else are we slowing down? Here from D to F. Notice that we're going from motion to stopped at F. So we have to be slowing down. And also beyond G, I see there's some slowing down there as well. But the only points that look to be on our intervals of slowing down would be A and E. Lastly, at what points is our object changing direction? Looks like B and F. Those would be the peaks and the valleys. They're the maximums and minimums. That's where we change direction. Now hopefully we can use all this information to sketch a decent velocity graph. We want to see here that the velocity is high. Okay, and then it's less and less and less. So we want the slope of the graph above to equal the value of the graph below. So here, it's very steep. So we want to start off high. Over here, it's less steep. So we could do something like this. Here we're starting off at a velocity of 0, and then we go more and more into the negative. And notice that it is quite steep here at D, and the object is traveling in the negative x direction. So we want to do something like this. Then we'll have it come back up. Goes back to 0 here. And it looks like it'll go up to a maximum steepness and then perhaps come back down. That'd be a decent graph for it. So wherever the slope is steepest, we want our velocity to have a high value. That's the connection between the graph above and the graph below. If we're at a point where the slope is less steep, then we want a low value. Now here we see that the position graph is steep in the negative direction, so we want a large negative value at this point. Here we have a local min, so we want our velocity to be 0 there, and it should be 0 here. Here we're at a pretty steep point at G, so we want a decently large value there. And there we go. That's a good velocity versus time sketch. It doesn't have to be perfect. It's just a guess. It's just freehand. All right, now we want to sketch the acceleration. And there's a guide for this on the previous pages. And the concavity of the position versus time graph tells us about the acceleration. So concave up is a part of the curve that looks like a smile. And when we have a smile, there is positive acceleration. Concave down could be considered a frown. And when that happens, we'll have negative acceleration. So this could be a useful fact. It'll help us sketch what we think the acceleration versus time graph might look like. Now over here we see that there's actually a frown face, and a frowning curve would indicate negative acceleration. We can also see that same idea because the velocity has a negative slope, and the acceleration is the slope of the velocity. So we want a negative value here. But eventually that turns around. That frown turns into a smile. And for a smile, we have concave up. And wherever there's concave up, we're going to have positive acceleration. We can also see that here with the velocity curve being sloped upward. So we want something like this now. At this point, it looks like we're going back to a frown for that interval, so let's go back to something like this. And we could connect them if we like. It's just a rough sketch. Now at some point there'll be a place where the frown turns into a smile. There's the frown, there's the smile. The point where they connect is called a point of inflection. It's where it's neither a smile nor a frown. It's in between. So what is the point of inflection for our graph here? Point D is the point of inflection. And that is going to be a place where the concavity switches from concave down to concave up. It's also a place where the acceleration switches in direction from negative acceleration to positive acceleration.